We're going to spend a little bit of time, actually quite a bit of time, talking about ionic bonding. Again, this was the bonding that occurs between a metal and a non-metal. And I asked you to think about why this would involve a transfer of electrons. Again, think about a metal. What do metals want to do? They like to give up an electron. Non-metals want electrons. And again, think back to why metals specifically want to give them up and nonmetals want them. And this results in an electron transfer from the metal to the nonmetal. So for example, let's think of potassium. Potassium is in the first column. It has one single electron. Here's its Lewis symbol. And let's think of chlorine. Chlorine is a halogen, has 7 valence electrons. And let's draw their electron configurations. I'll use kind of a little shortcut here. So there's the electron configuration for potassium. And here's the electron configuration for chlorine. Now, what do you notice about potassium? Well, if potassium were to give up its one valence electron and give it to chlorine, well, then potassium, which would become a cation, would have the electron configuration of argon. If chlorine were to accept that electron and become an anion, then it would have the electron configuration of argon as well. So I'll draw out that whole thing here just to show you. Both of them would have a filled valence shell. And so this is what we call ionic bonding, the transfer of electrons, and this forms an ionic compound. And this is the formula, KCl. You don't have to show the charges in the ionic compound, but you should know that this ionic compound is composed of a cation and an anion. Now let's do this for another compound. Let's take sodium with its one valence electron and try this with oxygen. And oxygen has 6 valence electrons. Now sodium has one extra and oxygen needs 2. Well, if this single sodium atom were to give its electron to oxygen, oxygen's still not happy. It still doesn't have a full octet. What else? It needs one more. So in order to have that filled valence shell, a second sodium is going to come along and give another electron to oxygen. So this results in forming 2 sodium cations and 1 oxygen anion. Notice what the charge of that oxygen is, though. It's 2 minus. Why is it 2 minus? Because it accepted 1 electron from one sodium and a second electron from the other sodium. So again, we have a cation and an anion. And the way we would represent the formula for this is we would use this subscript of 2 to indicate that there's 2 sodiums and then there's one oxygen. We're going to go through writing formulas a whole lot more, as well as nomenclature a lot later. And we're going to do a whole bunch of that. We're going to do that in lab. We're going to do that in lecture. So don't worry about mastering this like right now, but I'm kind of laying the foundation for it. Okay, well, let's do another example. Let's look at aluminum. Aluminum's got three valence electrons and have it combine with oxygen. So aluminum's got three extra ones, three extra electrons, and oxygen again needs two. Now you can kind of go through the math and start to realize, well, how many of each one do I need in order for everything to be, have a full octet? But let me give you a little bit of a shortcut. Notice aluminum has three extra electrons. I'm going to take that number three and do that. I'm going to take this number two and do that towards the aluminum. Now, why do I do that? Well, in order for aluminum and oxygen to be happy, to be in a stable compound, I need two aluminums with a plus three charge because it's going to give up every electron. And I need three oxygens with a minus two charge. Now I want you to highlight this. Look at that number three right there. That's that number three right there. And then look at this number two. That's that there. And you can kind of use this little kind of crisscross method to accurately write the formula for this ionic compound. And in actuality, you could do this with any ionic compound. Again, notice here we have a cation, something that's positively charged, and an anion, an atom that is negatively charged. Now, there is one catch to this kind of shortcut method. You always want to reduce to the lowest numbers, kind of like fractions. Now, what do I mean by that? Let's take a look at calcium. Calcium's got two valence electrons. And again, oxygen's got six. Calcium has two, oxygen needs two. And so calcium can give both of them to oxygen. But notice if I do the little crisscross thing, my formula isn't going to be Ca2O2. Okay, that's technically not correct. I'm going to reduce that to this to represent one calcium bonded to one oxygen. Now, before I move on, I do want to highlight something. You're going to hear me use a term quite often. Ionic compounds are also referred to as salts. So don't think of, when I use the term salt, don't think of just sodium chloride, because that's the salt that everybody's familiar with. But any ionic compound, all the ones that we've drawn on this page, we classify them as salts. Now, one thing I want to highlight right off the bat is that it's incorrect to call an ionic compound a molecule. So let's take sodium chloride, for example. And why is this? Well, let's compare sodium chloride to an actual molecule. For example, water. We're all familiar with that. So if we have a sample of water, it's just kind of floating around. and they might interact intermolecularly. I'll talk about those much later, like those what we call intermolecular forces, but they don't bond all to each other. But we can't say the same thing about sodium chloride. We don't have one thing of sodium chloride floating around individually from a second one, from a third one, and so on. That's not how um, ionic compounds associate with each other. In fact, ionic compounds form what are known as lattices or ionic lattices, where a single ion is bonded to many other ones. So let's take this kind of expanded lattice here of sodium chloride. The purple dots there represent sodium cations. The green dots represent chloride anions. And if you look right here, right in the middle at that sodium atom, notice it's bonded to a whole bunch of other chlorine atoms, or I should say chloride ions. So one sodium cation is bonded to many chloride ions. And that's really what an ionic bond is. You could say the same thing for chloride. You know, these chlorides here are bonded to a lot of sodium ions. And this creates very strong bonds. Now we quantify the strength of those bonds with the term known as lattice energy. Now we can look at lattice energy, the definition in two kind of like opposite directions. Lattice energy, you can look at it as is either the energy required to separate an ionic compound into its constituent gaseous ions, or you can look at the reverse process. It's the energy released when ions combine. It's describing the value is the same, it's just describing reverse processes. So, for example, when sodium ions combine with chloride ions, it forms sodium chloride. And the amount of energy that's released, we use this term called delta H. I'll dive deeper into that a little bit later. But right now, just kind of think of it, oh, this is a measure of energy, is negative 769 kilojoules per mole. I'll talk about what kilojoules are. I'll talk about moles are right now. I just want you to focus on that number, but not just the number, the sign as well. A sign, a negative energy, that's not a bad thing. That means it releases energy, which makes the compound more stable. Now, a term you'll hear me use for negative, like when energy is negative, is known as exothermic. And I'll dive deeper a little into that a little bit later, but exothermic just means energy is released. Now, as I said earlier, forming salts release energy, an exothermic process, and the result of that is more stability. So if I take sodium metal and chloride gas, it makes sodium chloride and releases energy. Now, that energy, or what we call from the previous page, lattice energy, is kind of difficult to determine. We have to go through a roundabout way to actually determine the lattice energy of an ionic compound. And this is where we use something known as the Born-Haber cycle. I'm going to introduce this now, and then in a few chapters, a few units down the road, I'm really going to dive deeper into it. So I'm going to do like a very cursory glance, and then we will dive a lot deeper later. But the Born-Haber cycle is a hypothetical series of steps that represent the formation of an ionic compound. So if you look at the reaction I drew above, sodium plus chlorine making sodium chloride, what the Born-Haber cycle does is it breaks that down into individual hypothetical steps. Each of those steps has a certain energy associated with it. Now, why do we care? The main reason is the Born-Haber cycle allows us to calculate the lattice energy of an ionic compound. And as I said, I'm going to dive a lot deeper into this in a little down the road, but let's just do a quick example of this. So what we're going to do is look at this reaction between cesium metal and fluorine gas to make cesium fluoride. Now, just a little side note, you notice that fluorine, I didn't draw just a single letter F. I have F2. Fluorine, all of the halogens, for example, and this is something to kind of put down in the margin of your notes or just kind of memorize this, put this in your head. All of the halogens exist as diatomic molecules. So all the halogens, fluorine, chlorine, bromine, iodine, they all exist as diatomic, F2, Cl2, Br2, I2. A couple others just to memorize, nitrogen and oxygen as well. Now, when cesium combines with fluorine to form cesium fluoride, CSF, it releases 553 kilojoules per mole of energy. Now, again, don't worry so much about what is this delta H, what is this F. The F there just represents formation. I made cesium fluoride, or I formed cesium fluoride from its elements. And I do want to highlight the importance of the sign. The sign is important because this means it released energy and became more stable. Now, I do want to highlight that this value, this is not the lattice energy. We are going to use that delta HF to find the lattice energy. So what this Born-Haber cycle does, I'll just say BH cycle, breaks this reaction into steps. And all the steps add up to that delta HF, that delta H of formation. So what are these steps? Number one, we're going to take each of our reactants, or we could take the cesium and the fluorine separately. The first thing that has to happen is we have to turn the metal into gas. This is a process called sublimation, going directly from solid to vapor or solid to gas without going through the liquid phase, without melting. That's called sublimation. So this is what that process looks like. We're going to take cesium solid, that's what that little lowercase s in the parentheses represents, and we're going to make it into gas. Now the energy required to do that, so this delta HS means how much energy it requires to sublime it. It is about 76 kilojoules per mole. And this is not a number I want you to memorize. These are numbers that I'd always give you if this is something I want you to do. But notice it takes energy. That's what the positive value means, is that energy has to be put in order to get that solid into a gas. And the second thing, let's deal with the fluorine. Because notice in the reactant there, fluorine is bonded to itself. Fluorine is bonded to fluorine, and I have to break that bond to get one single fluorine there. So that's what this second step is. I'm going to break fluorine, diatomic fluorine, into a single atom. So this is the process we're going to use here. Again, that requires energy. So the delta H in this case we call delta HBE, or bond enthalpy. Again, that's a term I'm going to highlight much later down the road. It just kind of refers to how strong a bond is. And it's positive because it requires energy to break that bond. Like I said, I want you to note that both of those processes, these first two steps, are positive values because they both require energy. Now, the third step, because I'm forming an ionic compound, I need to make sure both of my elements involved are ions. So I have to ionize the metal. And that's just simply using ionization energy. Remember that from our last unit? I'm going to take cesium metal. Now it's a gas. Give it energy to make the cesium cation, and it releases an electron. So that energy, that ionization energy required is 375 kilojoules per mole. Remember back when we talked about ionization energy, this is how much energy is required for an atom to give up an electron. You still have to put energy into it in order to form that ion. Now, I did this for cesium, I made it an ion. How do I do this for fluorine? Well, I got to give the nonmetal its electrons. Remember electron affinity? So fluorine, we're going to give an electron to and make it F minus, an anion. Now that actually is a negative number because fluorine just really, really, really wants that electron. So that releases energy. Now the last step in this cycle, now that we have our ions, okay, so ion here, ion here. The last step is I'm going to take those ions to form a lattice. So cesium plus fluorine minus is going to make cesium fluoride. Now, look at that reaction right here. And I want you to compare that to what I showed on the previous page. Let's see. Yes, this page here. When I talked about lattice energy. Notice I'm taking these ions and I'm making an ionic compound out of it. It's going to release some sort of energy, which we call lattice energy. The thing is we don't know what that is. The lattice energy, we don't know. But according to the Born-Haber cycle, all of this should add up to negative 553.5 kilojoules per mole. Where did I get that from? I got that here. So all of it should add up to this delta HF. So I have all of these numbers, and I have one unknown. Let's just put it all in a mathematical formula. So it should all add up to this. I'm going to take all the numbers I have. And then there's I have X. X is just my lattice energy that I'm going to solve for. So throw that all into a calculator. And that comes out to negative 756.9 kilojoules per mole. That is our lattice energy for cesium fluoride. Now, one thing I want to make a note of, and this is very important, maybe jot this down somewhere. The formation of a salt isn't favorable or exothermic just because a metal wants to give an electron and a nonmetal wants to get an electron. Okay, forming a salt is favorable. When I say favorable, I mean like more stable, releases energy. because the positive and negative attraction in the lattice is highly stabilizing. This value right here is a very large negative number. Again, negative's not bad. Negative means it released energy, and the end result was a lot more stable than what we started with.